So, we have been looking at goal stack planning, and the important thing to remember about goal stack planning is that it takes the goals that you want to achieve and attempts them in some linear order. So, if there are 2 or 3 goals, let us say G1, G2, G3, then it will attempt to solve one first, maybe let us say G1, then G2, then G3. And as we saw in the small example where there were 3 blocks A, B, C on the table and they had to be stacked with A on top of B, which is on top of C, that choosing the right goal order found the optimal plan, which was a 4-step plan. Now, let us see that for the same problem what happens when we choose a wrong goal order. So, this is the problem that we have. This given state is that all 3 blocks are on the table and you want B on top of C and you want A on top of B. Now, you can see that choosing the wrong goal orders, trying to solve on A B first is not going to be a great idea, because then you have to again clear B and then put it on top of C. But let us see how goal stack planning handles this. First, it pops that goal on A B. So, it tries to achieve that, and it does that by simply picking up A and stacking it on B. So, you have reached the state that where A is on B. Then it tries to achieve the second goal, which is to put B on C, and for that it has to unstack A from B, put it down again. So, that is taking it back to the start state here, if you notice. Then pick up B and stack it on C essentially. So, solving the 2 goals one by one in the wrong order did not achieve the final goal. After you solve the first goal, which is to achieve on A B, you got this picture here where you had A on B. Then when you independently try to solve on B C, that is the next goal, then you end up with a picture on the top where B is on C, but A is still left on the table. So, it has to, that is one of the reasons why we added the compound goal to this thing, because we check that it is not true, we push it back again, and then again this time it will see that it has a goal to achieve, which is pick up A and stack it on B. So, what goal stack planning found, if you had the wrong order in this particular domain, that you would find a plan, but it could be a longer plan. So, goal ordering matters essentially. So, in the tiny example that we saw, the wrong order resulted in a longer plan, but can it be that there are certain domains where it may lead to a dead end essentially. So, for example, if you are cooking something and you may have a plan in which you, let us say there is some vegetable which you want to peel and chop essentially. So, clearly peeling should be done before chopping essentially, and if you choose the wrong order, you will end up with a dead end essentially. So, which would of course mean that you would have to backtrack and try a different goal order, but that is something that we are trying to minimize or avoid. So, the question is that if you choose the right goal order, as we saw in the example, does it always result in an optimal plan? The answer sadly is no. Certain problems have non-serializable sub-goals essentially, which means what? It means that the 2 or 3 goals cannot be solved in a serial order. There is no optimal order for solving them essentially. Solving one may undo a previously achieved goal essentially. We saw that in the wrong choice of goals for the small problem, it undid we achieved first on A B, then we achieved on B C, but that undid that on A B. So, we had to attempt it again essentially. But for that problem there was a correct goal order, which was to first solve on B C and then solve on A B. What Gerald Sussman showed us was that there are problems where there is no correct order, and by that we mean that there is no correct order which will give us an optimal plan essentially. We have already seen in the case of 8 puzzle and the Rubik's cube, if you think of them as having sub goals, that for example, in the Rubik's cube you may have the sub goals that first achieve the top cross, then achieve the top layer, then achieve the middle layer, then the bottom cross and the bottom corners and so on. Going from one sub goal to the next, you have to undo the previous sub goal essentially, and we have looked at that problem. So, let us look at this example given by Sussman. It is also a very simple problem. On the bottom left, you can see the given state. C is on A and B is on the table, and you have to achieve A on B on C essentially. So, what is the correct order for doing this? Let us see. Let us say you first achieve on BC. That is done very simply. You pick up B and stack it onto C essentially. So, you see the figure on that, B is on C and C is on A. Then you attempt to do on AB. That requires more work. You have to first unstack B, put it down on the table, then you have to unstack C from A, put it down on the table, then pick up A and stack it onto B. But that results in the figure on the top where A is on B, but C is on the table. So, that is not the goal that you wanted. So, again you will have to do some extra work to reach the final goal state. What about the reverse order? Supposing we try to achieve on AB first. So, if you want to achieve on AB first, you would first unstack C from A, then put down C, then pick up A and stack it onto B, and you reach the stage which is where you have achieved on AB essentially. Then you say, okay, now I want to achieve on BC. Then you see that you have to unstack A from B, put it out on the table, then pick up B and stack it onto C. So, you have reached the state, but which is not the final state, because A is not on B essentially. So, neither order gives you an optimal plan. In both cases, you end up with a, supposing you have achieved two goals on AB, on BC. In any order, you do not end up solving the plan, which means of course, in this blocks world domain, you can do some more actions and eventually achieve it, but you will have a longer plan. What is the optimal solution for this particular problem? As you can imagine, you must first unstack C and put it down, unstack C from A and put it down. So, it should this is a mistake, this should be C. So, then you have all the three blocks on the table, and from there we can know that in 4 steps you can reach the solution. You pick up B and stack it onto C, and then you pick up A and stack it onto A essentially. So, that situation we are familiar with. This, as you can see, is a 6-step plan essentially. There are 2 actions here, 2 actions here and 2 actions here. Goal stack planning will not be able to find this 6-step plan, as we saw in the example essentially, because what this really involves is that, let us say we want to choose in this order, on AB first and then on BC. So, you start with trying to achieve on AB. So, you unstack C from A and you put down C. So, that means you are in a state where everything is on the table. At this point, you need to shift focus to achieving on BC first. Essentially, we can see that, goal stack planning cannot see that, and in fact, goal stack planning tries to solve them in a linear order. So, it will say, okay, if I am starting on AB, I will first achieve on AB, then I will go to the other goal which is on BC. But what this really needs is that midway through this process of trying to achieve on AB, you shift focus and go back to on BC. So, what is the means? So, this is a state that you are in, and that is where you are shifting focus. So, to achieve on BC, it is simple, pick up B and stack it onto C essentially. So, that will take you to the state which is shown on the top here, that you have stacked B onto C and this thing. And now you can come back to your original goal of achieving on AB. So, you pick up A and stack it onto B and you will have achieved the goal. So, you can see that this is the same 6-step optimal plan that we saw a while ago, but it requires the planner to be more flexible. It should move away from this strict saying that I will only achieve first one sub goal and then I will go to the next sub goal. You have to somehow mix up things essentially. And what Sussman showed was that there were many problems which had non-serializable subgoals essentially. And Richard Koff had also spoken about it when he was talking about solving the Rubik's Cube and things like that. What Sussman did was to give us a small problem which is called Sussmans Anomaly. So, next we will start looking at how can we look at other approaches to planning which are not linear planning, in the sense that they do not do things in a linear order, but can do in different orders, and that approach is going to be plan space planning.